elusive white hole has finally been discovered in a groundbreaking revelation that has sent ripples through the scientific community. This monumental achievement, the result of persistent exploration and research over many years, has opened up a new chapter in our cosmic odyssey. A white hole is a hypothetical celestial phenomenon, often portrayed as the mirror twin of a black hole. The discovery of this enigmatic entity presents a pivotal question. How does this game-changing discovery impact the field of astronomy and reshape our perceptions of the universe? In outer space, black holes are like the universe's hunters. They have very strong gravity, and they are constantly wanting more stuff to devour. They hide in the vast expanse of space, ready to consume any matter that dares to cross their path. However, their less familiar counterparts, the elusive white holes, hold an equally mesmerizing allure, wrapped in an enigmatic shroud of mystery. Imagine black holes as the voracious consumers of cosmic matter, and then picture a white hole as the exact opposite, a celestial body that expels matter into the universe. Many of us knew about black holes or know about black holes, those cosmic hunters that move through the universe and gobble up anything that comes into their path. But there's another interesting and mysterious idea in astrophysics called white holes, which are less famous, as you already know. To understand white holes, it's first important to understand black holes, because they are mirror images of each other in many ways. So let's take a moment to delve into the shadowy world of black holes before we explore white holes. Wink, wink. Despite their vast variety in size, black holes can be generally categorized into three types, based primarily on their mass and size. Smallest among them are the primordial black holes. Although they may be as minuscule as an atom, they could potentially pack the mass of a colossal mountain with their infinitesimal confines. The next category is the stellar black hole, which is essentially a medium-sized black hole. A stellar black hole, though not excessively massive, can still accumulate about 20 times the mass of our Sun within a spherical space of just 10 miles in diameter. This incredible density of matter enables them to wield a formidable gravitational pull. Our very own Milky Way galaxy is speculated to host numerous stellar black holes. The most massive black holes are designated as supermassive black holes. These cosmic behemoths can be more massive than 1 million suns combined, but could theoretically fit within a sphere the size of our solar system. Each large galaxy, including our Milky Way, is believed to harbor a supermassive black hole at its heart. For instance, nestled deep within the grand tapestry of the cosmos, at the heart of the Milky Way galaxy, dwells a titan by the name of Sagittarius A. This is no ordinary celestial body. Sagittarius A is a supermassive black hole, a region of space-time where gravity is so powerful that nothing, not even light, can escape its grasp. This gargantuan entity, with a mass of around 4 million times that of our Sun, lies approximately 27,000 light-years away from Earth, silently reigning over our galactic neighborhood. But Sagittarius A is not alone in this class. Far across the vast expanse of space, some 3,000 light-years away, another such phenomenon, Rho Apuici A, commands its domain. It's an even more massive entity with a staggering mass of about 10 million times that of the Sun. This celestial behemoth is a testament to the grandeur and the mystery of our universe. Venturing further into the cosmic abyss, we encounter NGC 1277, a distinct galaxy that houses a supermassive black hole with an incomprehensible proportion to it. With a mass roughly 100 billion times that of the Sun, this black hole is one of the most massive objects ever discovered. NGC 1277, perched at a mind-boggling 2.7 billion light-years away, is a testament to the scale and the splendor of the cosmos. Our journey through the universe takes us even further, to JO313-1806 and J2150-0551, two supermassive black holes that dwarf even the massive giants that we've already encountered. These black holes, with mass of about 21 billion and 30 billion times that of the Sun respectively, are positioned about 3.9 and 10.9 billion light-years away from Earth. Their discovery expands our comprehension of the universe's potential for enormity and power. These celestial behemoths are but a handful of the numerous supermassive black holes scattered throughout the universe. These extraordinary objects not only captivate our imagination, but also provide valuable insights into the nature of our cosmos. And yet the universe is not solely composed of these gargantuan entities. In the shadow of these supermassive black holes, smaller ones exist. Stellar mass black holes, the smallest of the lot, result from the collapse of massive stars, bearing masses 10 to 20 times that of the Sun. But on the other hand, intermediate mass black holes boast a mass between 100 and 10,000 times that of the Sun. Despite their size, these black holes are no less intriguing and pivotal to our understanding of the universe. In all their variété and mystère, Black holes are among the universe's most intriguing riddles. While we have yet to fully decipher them, each discovery peels back a layer of this cosmic onion, edging us closer to comprehending the true nature of gravity and the true nature of the cosmos, if that even is such a thing. As we continue our celestial exploration, these cosmic entities serve as reminders of the grandeur, of the complexity and infinite mystery of this universe that we inhabit. It's a gift. Doesn't always feel like it, but anyways. Black holes are believed to originate from various cosmic processes. Primordial black holes are thought to have formed shortly after the Big Bang. Stellar black holes are thought to be the result of the implosion of a massive star's core, a catastrophic event that can trigger a supernova, hurling stellar debris across space. Supermassive black holes and their host galaxies are hypothesized to have co-evolved, with the black hole size correlating with the galaxy's overall mass and overall size. Now back to the topic of white holes. Just as a black hole's immense gravitational pull swallows everything that comes within its event horizon, a white hole, in stark contrast, is theorized to expel matter from its event horizon. Although no observational evidence of white holes has been found until now, their existence is mathematically plausible. This latest discovery marks a significant milestone in our quest to understand the universe's mysteries, promising to illuminate our path towards uncharted territories of cosmic knowledge. Black holes, cloaked in an aura of mystery, are invisible to the naked eye, their overwhelming gravitational forces prohibiting even light from escaping their clutches. However, astute scientists have observed that their potent gravitational influences on nearby stars and gases are an observable effect. By meticulously scrutinizing the orbits of these celestial bodies, researchers can discern the invisible presence of a black hole lurking in the shadows. A fascinating spectacle unfolds when a black hole and a star maintain a close orbit. The intense gravitational interaction between two celestial bodies emits light of exceedingly high energy, detectable by state-of-the-art scientific instruments, and given enough time and the right circumstances, a black hole can gorge on a star's outer gases to form an accretion disk around itself. As the gas from the accretion disk spirals into the black hole, it's heated to astronomical temperatures, radiating X-rays in all directions. NASA's sophisticated telescope captures this X-ray radiation, providing invaluable data for astronomers to unravel the enigmatic properties of black holes. But there is a question that might have crossed your mind at this point. Will our sun collapse into a black hole? The answer, simply put, is no. Our sun lacks the requisite mass to collapse into a black hole. However, this doesn't imply that our sun is immortal. Billions of years from now, the sun will exhaust its nuclear fuel, swelling into a red giant star. Following this fiery phase, it will shed its outer layers, transforming into a planetary nebula, a glowing shell of gas and dust. Ultimately, when this happens and it's expended all of its energy, the sun will cool down and settle into its final state, a white dwarf. But there's no need to lose sleep over this. It's unimaginably far in the future. Would never happen, but by the time it does happen, you can almost guarantee we're going to be interplanetary, so anyways. Now, let's shift gears and delve into the world of white holes, often dubbed as the cosmic twins of black holes. Picture a white hole as a black hole rewound, an echo from a distant past. A black hole's immense gravity ensures that any matter crossing its event horizon is forever lost to the cosmos. In contrast, a white hole represents a region of space-time where matter is perpetually expelled, and time expands indefinitely in all directions. Theorists postulate that a white hole could emit light with the same intensity as a black hole, but with a crucial difference. The outgoing radiation could potentially be lethal. Any attempt to venture into a white hole would be tantamount to suicide, as the intense gamma radiation would obliterate both the crew and the ship. Even if, for the sake of argument, we were to imagine a ship robust enough to endure this onslaught, the white hole's surrounding space-time structure would necessitate an increasingly greater acceleration as one ventures closer to its heart. In essence, no amount of energy in the universe would suffice to penetrate a white hole. It's like trying to fully clasp two magnets together. Or, the opposite sides of magnet. You get what I'm saying. Any attempt to do so would be an exercise in futility, a cosmic odyssey destined to fail. The concept of white holes, an intriguing counterpart to black holes, was born out of mathematical curiosity and the relentless pursuit of knowledge, as, humans do sometimes. The roots of this theory trace back to 1905, when the brilliant mind of Albert Einstein deduced the perception of time varies between observers who are stationary or moving at a constant speed, and those who are accelerating. Furthermore, Einstein posited that the speed of light remains constant, unaffected by external influences. This idea was later encapsulated in Einstein's monumental general theory of relativity, where he revolutionized our understanding of gravity. According to him, gravity was not an actual physical force, but rather a manifestation of the warping of space and time caused by massive objects. Building upon Einstein's field equations, Carl Schwarzschild subsequently derived an equation to describe mass in empty space-time. The resulting metric, known as the Schwarzschild metric, serves as a complex mathematical representation of a black hole. This equation depicts a static, uncharged black hole, a celestial object that has always existed at its current size. One key point to understand is that all events in a black hole occur at or beyond its event horizon, and from an outside perspective, it appears as if such an event never will transpire. According to the Schwarzschild metric, space and time swap roles within a black hole, making its singularity an inevitable point in the future, not some location. If you were to trace back the life of a real black hole, you'd discover a dying star at its inception. Interestingly, if we reverse this narrative, we end up with a white hole instead of a black hole. The discovery of a white hole is incredibly significant, considering not all scientists have previously, agreed that they were even real. So, why do some scientists remain skeptical about the existence of white holes? Well, their skepticism arises from the belief that mathematical consistency with general relativity is not sufficient to validate a white hole's existence as legitimate scientific theory. Which is why, in the words of some researchers, observing a white hole with a telescope remains an impossible possible. Although the existence of white holes cannot be categorically denied, empirical evidence remains elusive. This skepticism is grounded in the second law of thermodynamics, which dictates that entropy, or disorder, of the universe must either remain constant or increase. Despite its negative connotation, entropy essentially represents the growth in the number of possible particle states within a system. Picture a house demolished to rubble. This scenario epitomizes increased entropy, as the wreckage could be rearranged into numerous structures, like sheds, bookshelves, or mounds. Similarly, the particles making up the house could assume other countless configurations, besides forming a house. When applied to white holes, this principle further fuels the ongoing debate about their existence. The principle of entropy, or the degree of disorder in a system, holds a crucial place in our understanding of the universe. According to the second law of thermodynamics, while local decreases in entropy are permissible, the overall entropy of the universe must consistently rise. Black holes play their part in this cosmic rule by spreading low-entropy entities, such as planets, across vast distances and enormous time scales, thereby enhancing the universe's disorder. White holes, however, appear to defy this principle, as their own massive outflows could potentially decrease global entropy. This underpins physicists' assertion that time cannot be reversed. Despite the seemingly contradictory behavior here, the existence of white holes is not completely ruled out. Theoretical physicist Carlo Rovelli, for instance, postulated a fascinating hypothesis. You see, my man proposed that when black holes reached a point where they can no longer evaporate and contract due to constraints of spacetime, they experience an outward pressure, or a quantum bounce, morphing into white holes. Following this transformation, black holes rapidly evolve into white holes. Nonetheless, due to the effects of gravitational time dilation, we as external observers would continue to perceive it as a black hole, even after billions of years have passed. Rovelli's theory further suggests that primordial black holes could potentially decay at any moment, emitting a burst of radiation analogous to cosmic rays. An event in 2006 might offer some hint of this phenomenon. NASA's SWIFT satellite detected a particularly bright gamma-ray burst in an unexpected sky region, labeled GRB 060614. Gamma-ray bursts are typically classified into short and long durations, with the latter often associated with supernova. However, GRB 060614 defied this categorization. See, the peculiarities of GRB 060614, never going to get tired of saying that, left astronomers scratching their heads. Despite its astonishing duration of 102 seconds, considerably longer than the average gamma-ray burst, which typically lasts around 30 seconds, it displayed zero connection to the stellar supernova. Furthermore, the host galaxy of GRB 060614 had a dearth of stars capable of actually producing such extended bursts of explosions. This puzzling gamma-ray burst seemed to emerge out of the blue, only to fade away almost instantly. Such phenomena challenge our understanding of the universe and may potentially serve as the elusive evidence needed to validate the existence of white holes. However, much like the mysteries that they're born from, white holes remain enigmatic, urging us to push the boundaries of our knowledge and explore the uncharted terrains of the cosmos. Several years after the anomalous event of GRB 060614, scientists proposed a rather radical yet intriguing possibility. Could this event have been a manifestation of a white hole? This hypothesis was not randomly conceived, but was, in fact, the result of careful observations and deductions. The unique characteristics of GRB 060614 seem to align with the textbook definition of a white hole. What are these characteristics, you might be asking me, Mr. YouTube man? Well, GRB 060614 displayed an immense yet transient burst of matter and energy, indicative of the behaviors theorized for white holes. Furthermore, the source of this gamma ray burst appeared to originate from a point too minuscule to be visually detected, another feature consistent with our theoretical understanding of white holes. The intrigue surrounding this hypothesis is deepened by the fact that it emerged as a compelling explanation after the best available scientific models systematically ruled out all of the other possibilities. In the face of phenomena that defy conventional understanding, this hypothesis stands as a testament to the relentless pursuit of knowledge, the relentless quest to unravel the mysteries of our universe. So what do you think about white holes? Do they exist as exotic entities in our universe, or are they just mathematical curiosities with no physical counterpart? Let us know your thoughts in the comment section down below. Don't forget to give us a like and subscribe for more. Bye!